Hello everyone, welcome back to Science Icons once again. So today we are going to proceed with the last part of the chapter that we have already started, that is pulley. Now before we proceed, we have to know one thing, why are we learning this? Because pulley is a part of simple machines. But it's a bit unique, Why? That you will understand while I proceed further. But understand one thing, all the simple machines that I have told so far, if you have seen my part 1 and 2, all the videos that I have made, I'll give the link in the description. There you will find I have told some machines to have mechanical advantage greater than 1. Some machines had mechanical advantage lesser than 1. If it is greater than 1 mechanical advantage, what are we calling them? Force multiplier. If the mechanical advantage is lesser than 1, what are we calling them? Speed multiplier. But here in case of pulley, you will find a kind of pulley where the mechanical advantage is neither greater than 1 nor it is lesser than 1. What we will call them? It is neither force multiplier nor speed multiplier. What we will call them? At that point of time, we are going to neither call them force multiplier nor we are going to call them speed multiplier. What we will call it? That you will understand if you proceed with me further. So let's begin. Pulley is basically nothing but a grooved rim. Like I've said, what is a lever? Lever is nothing but a rod. Similarly, pulley is nothing but a grooved rim. Around this grooved rim, I hope you all know the meaning of grooved. Around this grooved rim, what we are hanging? We are hanging 2 strings. Okay? Around this rim, we are hanging strings. Now, what did I say 2 strings? Because we have to take 2 sides. Actually, the string is 1. There is only 1 string. But we need to have two sides of the string. I should not say 2 strings, but we need to have 2 sides of the string. It's not like the structure cannot be like this. Okay, only one side the string cannot be there. Okay. So we need to have strings on both the sides, and what we have to know one thing is that one side we have to apply the load and another side we have to apply the effort. So let this side be load. Apply the load in the sense we will hand the load, and from another side we are going to apply the force, that is going to be your effort. Fine. This is what rim is all about. And how is it getting supported? There is an axle in the middle from where we are hanging it to a strong support. Clear? Now when we talk about pulley, we have to know that there are 2 types of pulley. One is a single fixed pulley. Another is a movable pulley. So one is a single fixed pulley, another is a movable pulley. Now what is a single fixed pulley? Let me read it. A pulley which has its axis of rotation stationary in position. What is axis of rotation? I have already covered in my previous part. Still, for here, let me tell you, the axis of rotation is the axis around which a circular body or anything is rotating. Fine. For here, the axis of rotation will be this part. Okay. What it is saying here? The pulley which has its axis of rotation stationary, that means it will be at rest. It will not move. So the axis of rotation will not move. It's stationary. It is fixed. And it is fixed in its one particular position. Fine. Now this pulley which I have drawn is nothing but a single fixed pulley. Whenever someone asks you to draw a pulley, if you know what is a pulley, if someone asks you, draw me a pulley, we will always try to draw this. Okay, this is the simplest form of pulley. Henceforth, whatever example in the beginning you will find in your book are all single fixed pulley. They're all simple. Rarely people can think about movable pulley, but yes, it does exist, but we rarely think about it. Normally when someone asks us, draw me a pulley or show me how a pulley looks like, we tend to draw this. Okay, so refrain from only drawing this, because movable pulley also exists. Now let me read out one thing. Here the load and effort, both the things are acting downward. You can see here, both the things are acting downward, but the tension throughout the string, if we assume it to be T, is same, which is acting upward. That means this side we are having the effort downward, tension is acting upward. This side load is acting downward, tension is acting upward. Both the side tensional force is acting where? Upward. Fine. What is tensional force? I have already said in my previous part. Do watch it out. Now it is the force due to friction between the string and the surface of the rim of the pulley which rotates the pulley when the string is pulled down. That means if I am pulling the string of the effort, the load is going to move up. Why? Because there is a frictional force that is always existing in between the rim and the string. Due to that force of friction, whenever we are pulling the string of the effort, the load moves up. Okay? And the tensional force is always acting downward. Wherever or in whichever direction we are applying the force, tensional force is always going to act against it. Here I am pulling it downward, tensional force is acting upward. Here also load is moving downward because load, gravity with weight. What is weight? The force with which gravity pulls you down towards its center. So load is getting attracted by the gravity, it is pulled down. Weight is acting over here, that means force is acting downward. Henceforth tensional force is acting where? Upward. Fine. Now we have to know what is the mechanical advantage, velocity ratio and efficiency of a single fixed pulley. Now if we neglect the mass of the string and friction at the axle, what we are assuming these kinds of situations where we are neglecting. So first of all what we are doing single fixed pulley. In this single fixed pulley, let us assume that the string is negligible in mass and there is no frictional force acting. So let the string have negligible mass and let there no frictional force acting. If we assume these two things, then the situation that is going to arise is known as ideal situation. That means in our calculation, in understanding concepts, there is not going to be any exception. We are not going to face any difficulty or hindrance. Okay. So this is the ideal situation that we are going to assume and then proceed with further concepts or calculations. Fine. Now, when we talk about mechanical advantage, it is what? Load by effort. And with respect to effort arm and load arm, what is the formula? Effort arm by load arm. Let me write it once again. For detailed explanation again, watch out the previous part. So mechanical advantage is equal to load by effort, or we can also say it is equal to effort arm by load arm. This is what mechanical advantage is all about. Now here we have to know one thing. Load is equal to tension. Why? Because if you are applying, suppose this is the string. If you are applying 5 Newton force downward, tension force that is going to act will also be equal to 5 Newton. You have to understand this. The force with which you are pulling the string downward, the same amount of force is going to act as the tensional force. That means if you are pulling it with 5 Newton force upward or in upward direction, tensional force is going to act, which is also equal to 5 Newton. Fine. Henceforth, here load will be equal to tension. Now, if we consider this side, effort will also be equal to tension. Thus, from the two equations, we can say that is, if we take these two equations as 1 and 2, and if we calculate from equation 1 and 2, if we calculate, if we replace T, then we are going to get load is equal to effort. Load is equal to effort, which is in turn equals to T. Fine. Now mechanical advantage is what? Load by effort, which I have already written. Load is equal to T, E is also equal to T. So can I write T by T? I can write this. it will get cancelled out. Finally, we will be left with 1. So mechanical advantage will be equal to 1. Fine. Now let us come to velocity ratio. Now you have to activate your imagination power. Imagine, okay, truly imagine. If you have the practical setup at home, very good. Try it practically, but here I cannot show you practically I cannot show you. So imagine, if I apply a force on the, or if I apply effort on this string and moves it by distance d, or rather it is performing a displacement which I am assuming it to be d. Okay, that means it is moving d meter down. This string is moving d meter down. Automatically this side the string is going to move up by d meter. By d meter, automatically the string is going to move up. Again I am saying, this side we are having the effort. I am pulling the string. It is having a displacement of d meter. Automatically this side the load is going to move up. How much displacement it will be covering? D meter. Since this side we are displacing it by d meter. So this side also the displacement will be by d meter. This is the thing. Now velocity ratio is equal to what? We know the formula. We know the formula very well, that VR, that is velocity ratio, is nothing but it is equal to the displacement made by the effort, displacement made by effort by displacement made by load. If displacement made by effort is d, that means displacement made by load is also d. D and d gets cancelled. Velocity ratio also comes to be 1. Now mechanical advantage was 1, velocity ratio is 1. What is efficiency? What is efficiency? It is nothing but mechanical advantage by velocity ratio. Mechanical advantage by velocity ratio is my efficiency, which we represent using eta. This is what? This is efficiency. We represent it using eta. Mechanical advantage is my 1, velocity ratio is 1. That means together it is 1. And we can say that efficiency is 100%. If I multiply this into 100, in terms of percentage we will be able to find out. So it is 100% efficient. Now why it is 100% efficient? Because we have assumed it to be an ideal situation. Normally none of the machines are 100% efficient. Okay, there are situations or there are circumstances which will arise that will automatically pull down the efficiency rate. Fine. Now the question arises. Mechanical, that I have said in the beginning of my video. Mechanical advantage can be greater than 1, mechanical advantage can be lesser than 1. If it is greater than 1, then it is force multiplier. If it is lesser than 1, then it is speed multiplier. But here mechanical advantage is equal to 1. It is neither force multiplier nor speed multiplier. Then what is it? Let me clarify. Mechanical advantage here is equal to 1. That means it is neither greater than 1 nor it is less than 1. So we can neither call it force multiplier nor we will call it speed multiplier. Rather, nor we can call it speed multiplier. So we will call it nothing. Basically, pulley is used to apply force in convenient direction. Like for example, scissor. You are using scissor to cut a page or any cloth, piece of cloth, whatever, with speed. That's why it's a speed multiplier. There are many examples where it is acting as the force multiplier. Here it is neither helping you to multiply the force. That means you are applying small amount of effort, larger amount of output, or in that case you can also say in this way, you are applying small input or giving small input, you are getting large output. Here you will not find that kind of a thing. Moreover, you will not able to multiply speed here. So what you can do using pulley, you can apply force in a convenient direction. Okay. Now, why are we calling it that effort can be applied in a more convenient direction? Why are we saying it? Because it is, I'm just reading out from the book because you will find keywords over here. Then I'll explain you. It is difficult to apply effort upward to lift a load directly. Like for example, let the load be here and you're trying to pull it up by applying effort upward. Of course, I'm sure you'll be able to feel how difficult it will be to lift the load like this. You'll be able to feel it. So it is difficult to apply effort upwards to lift a load up directly, but it becomes easier with the help of a fixed pulley because the effort can now be applied in a downward direction to raise the load up. Further, to apply the effort downwards, one can conveniently use one's own body weight for the effort. That means if you are applying downward, if you are applying it upward, only the effort that you can apply using your muscles, only the effort that you can apply with your muscles is going to act here. But if you are pulling it downward, you can use your full body weight. So it becomes much more convenient. That's why pulley is helping in applying the effort, the force, the input in a convenient direction. It is neither helping you to multiply the speed or multiply the force. Clear? After this, let us proceed with single movable pulley. Now what is a single movable pulley? Where the axis of rotation is movable, that is, it is not fixed in a particular position. So far, I hope that you will have understood what is the axis of rotation. I have already said. So here pulley whose axis of rotation is movable. So in case of movable pulley, what is happening? So axis of rotation is fixed or movable. Not fixed or movable, right? That means we can draw it like this. This is the fixed support. This is the axis from where the load is hanged. This is the way using which, or this is the way how you draw a movable pulley. Applying effort. Fine. Now since effort is applied upward, that means load is getting applied downward, tensional force is also going to get applied upward. Since load is getting applied downward, so tensional force is going to act upward. Now you will say that in case of single movable pulley, here effort is getting applied upward. It will become difficult for us again. It will not be a convenient mode of applying the force. Of course, for that we have a solution. But this is what a typical movable pulley looks like. Fine. Now here load is getting supported by two tensional forces. Here load is getting supported by two tensional forces and effort is getting supported by only one tensional force. Right? Hope you can understand this. Now, if I have to find out the mechanical advantage here, then we can say again load by effort. Here load is what? 2T. This is what? T. PT gets cancelled. So mechanical advantage is equal to 2. Fine. After this, we have to know one very simple thing. Very simple, but if you are not understanding it, if you are not trying to understand, it becomes difficult. Suppose we are pulling the effort string and causing a displacement of D again. Okay. If this side we are applying D, then from this side also D string is going to be used. Or suppose, let us make it more simple. If D meter of displacement is caused due to the effort which is getting applied in the string, then the load is going to be lifted by D by 2 meter. Load is going to be lifted by D by 2 meter. That is, if it is traveling 2 meter, the load will be moved by only 1 meter. Half the displacement which is caused by the effort string, or which is happening with the effort strain. If I am applying d meter of displacement here, load is going to move by d by 2 meter. Now velocity ratio is equal to what? dE by dl. What is my E? E is d. What is my load? Displacement of load? It's d by 2. Let me move d into 2 by d. This is the calculation. So again, VR is coming to be 2. Now if I have to find out the mechanical advantage, if I have to find out, sorry, not the mechanical advantage that I have already found, the efficiency, MA by VR into 100, this 2 by 2 into 100, that is equal to 100%. Fine. Now again, why it is 100%? Because we have assumed it to be an ideal situation. Again, I am saying it is not possible to get 100% efficiency in any simple machine. There will be frictional forces acting. Fine. Now what is the solution for this? That I have already, the problem that arose, that effort we are applying it upward, we can only apply the power of our muscle. We cannot use our own body weight. So it's not a convenient mode of applying the convenient direction for applying the force. Henceforth, this is going to be the last topic, that is solution to this problem. What is the solution? The solution is very simple. What was my diagram basically? What was my diagram? This is my diagram. There we are having a rigid support, one pulley, string is getting fixed here with a rigid support, the string is fixed, this side we are having the load hang, and we are applying the effort upward. Now instead of applying the effort upward, we are going to use a single fixed pulley here. What we are going to use? We are going to use a single fixed pulley. And then apply the effort. Okay? So this side we are having, so this is a fixed as well as movable pulley. So whatever we are using here is having both movable as well as single pulley. So this side is movable and this is fixed. And we are using a combination of both. Fine? Now again the effort is getting load is getting supported by one tensional force and then here another tensional force. And effort is getting supported by only one tensional force. Again, if I have to find out the mechanical advantage, you can find out here it's 2t, here it's t. Again the mechanical advantage will stand out to be 2. You can find out velocity ratio using the same process as well as find out the efficiency. Telling you the formulas once again. MA is equal to load by effort. VR is equal to distance moved by the effort by distance moved by the load, and efficiency eta, let me write it down, efficiency eta is equal to MA by VR into 100%. Fine? So this was all regarding pulley. Another part is left, that is block and tackle. That particular portion you will find in my short section. It's very simple. I'll not make a separate video on this, rather in short section within 1 to 2 minutes I'll be explaining you. Maybe in different parts I'll not be able to cover in one shot, but I'll explain you there. So this was all, but the last thing that I want to tell you is regarding this ideal situation. Whenever you are going to perform or solve any numerical, if the question says in ideal situation, then you will assume it to be ideal situation. If the question says nothing, again you will assume it to be an ideal situation. But sometimes the question will state that friction of 2 Newton is getting applied. At that point of time, remember to subtract 2 Newton, because 2 Newton of force is getting lost as friction. So 2 Newton force is not getting, efficiently being worked. Okay, the 2 Newton force that you are applying is not getting worked here. It is getting lost as the force of friction. Henceforth, at that point of time, you will have to subtract it. When we proceed with doing numericals, I will make a separate video, as I have already promised you people. There you will see different varieties of questions. And you are going to face such terms: ideal situation, frictional force, energy loss, dissipation of energy, and etc. Okay, so this was all for today. Do like, share and subscribe. If you have liked it, also press the bell icon, and stay tuned for the short section where I am going to explain you block and tackle and help you people solve few numericals. Till then, bye.